In this class we're going to look at data preparation and preliminary analysis. So when we have a set of figures, perhaps sales figures or production figures or figures related to market research or whatever, when we have a set of figures we wish to prepare the data for subsequent analysis. We need to be able to organize the data and to perform an analysis which turns the data into information, which enables us to make informed decisions. And this is our preliminary analysis. Now let's look at some of the techniques involved here. First of all, we would start by editing the data. And the editing process, well, this is used to detect errors and omissions, to look for errors in the data, perhaps gaps in the data, to see if the data collection was correct or if the data was entered correctly. So looking for errors and looking for problems in the data. And the editing process also corrects these if possible. It certifies that minimum data quality standards are achieved. So the editing process really looks at the data and based on its analysis, based on analysis at this early stage, can say yes, this data may be used for subsequent decision purposes, or perhaps no, this data is not recommended for future use because it's not reliable or there are gaps or issues involved in it. So it certifies the minimum data quality standards that are to be achieved. Now editing, it aims to ensure that the data is accurate. That's most important. It's consistent with other information, that it does not make claims that is not consistent with what we know from general facts. So it's consistent with other information sources. So for example, sales coming up to Christmas time may increase, and other sources of information may suggest this. So the data we're looking at for analysis in this case should suggest roughly the same thing. It should be consistent. And it should be uniformly entered. It should be collated in a uniform manner so that it's used easily. It can be extracted easily and used easily. So it's uniformly collected. It should also be complete. In other words, there shouldn't be gaps in the data. Ideally, it should run consistently through the whole set of data. There shouldn't be big gaps where information is missing. Ideally, it should be complete. And it should be arranged to simplify coding and tabulation. So the editing process should look at the data and be able to restructure the data so as to enable it to be coded. Coding is important because it makes the analysis easier later. So that, for example, with questions in questionnaires, a question such as, do you buy this product every week? That could be given a code of 1. Do you buy this product every 2 weeks? That could be given a code of 2. So computers can be used then to analyze 1s and 2s, where the 1 equals buy the product every week and 2 equals buy the product every 2 weeks, and so on. So editing may be used to codify the data. Now, as I said, the questions may be coded for easy analysis. Of course, encoding could also use optical scanning. For example, an answer, I purchase this product every week, if that's given a code of 2 or 3 or 1 or whatever, then the 1 could be optically scanned, so that results from questionnaires of that type, if there are many questionnaires, may be optically scanned and therefore easily entered into tools for analysis. For example, the statistical package for the social sciences, or some such package where the results could be statistically calculated. It could be entered into, for example, spreadsheets as well, where a lot of data analysis can be performed, particularly with the increasing sophistication of spreadsheets. And we also bump into this term of data warehousing. A lot of data may be contained in databases. It is data, and it may be extracted from the databases. This will be known as data mining. And extracting it means transforming it and cleaning it, making it useful. Cleaning means making the data useful for subsequent analysis, and looking at what tools could be used for that subsequent analysis. So data warehousing is where data may be kept in different databases, and data mining means extracting the data so that it can be used later for analysis. And of course it may also buy data. Data may be purchased in convenient amounts or in convenient ways, which makes it easy for data entry purposes. Now, the area we're broadly concerned with in statistics is called descriptive statistics, and this looks at areas like I've got on the slide at the moment, such as distribution, standard normal distribution, central tendency, which means the mean, the median, the mode, the variability of the data, the variance, the standard deviation, the range, the interquartile range, skewness, and something called kurtosis. All of these terms we meet when we deal with statistics and we look at statistical issues. And it's important to have some understanding of what's meant by these different terms when we consider the study of statistics. So what is a distribution? What is meant by the standard normal distribution? What is whatever a mean, a median, or a mode? And what's meant by range, standard deviation? What's an interquartile range? So it's looking at all of these issues that constitutes the study of statistics. And you should really make a note of these and attempt to have some research done into them. There's a lot of information online giving background into what's meant by each of these. So pull out the terms here. Just go to a search engine such as Google, for example, and type in what is meant by standard deviation, or type in what is meant by interquartile range, and make your own notes and pad it out so you have got a complete set of notes. We'll be covering these terms in the course of the classes, but nonetheless it does no harm to do your own research and to make your own notes. Now, there are techniques to display and examine distributions. For example, a frequency table, and we'll be looking at those later as well, and histograms, which display all intervals in a distribution, even without observed values. And we can use a histogram to look for skewness and kurtosis and the modal pattern. Modal means the most common encountered observation, the one that we meet most often. That's the modal term. The modal term is the one that appears most often in a set of data. So we use a histogram to look at those. We could also use what's known as a stem and leaf display, and I'm going to spend a little time just looking at stem and leaf because it's very simple and yet it's quite useful. So let's just have a look at stem and leaf. Well, all it is organizing data with a stem and a leaf, as it suggests. So if we look down the stem here, I'll just put the cursor onto the screen. If we look down the stem here, we've got a 0, 1, 2, 3, 4, 5. In other words, it's like counting in tens. And the leaf is 3, 6, 9. So we have to have a key to tell us how to use the stem and leaf. And the key here is, say, 3 and a bar 6. Now that means in this case 36. So now we've got a key. We can interpret what's meant by this stem and leaf. So it seems like the numbers in the stem are in tens and the numbers in the leaf are in units. So for example, the one indicated here represents the number 12. We have 110 and we have the number 2, so we have 12. So it's quite straightforward to follow. I mean, that one is indicated as 46, a 4 and a 6. So if we take any row, say we take the first row here, it's 0, 3, 6, 9. That's the row 0, bar 3, 6, 9. And this represents the numbers 0, 3, 0, 6 and 0, 9 across there. So I think that's very, very straightforward. Here we've got an example. How many items are greater than 3 and less than 4? Well, greater than 3. So we look at the row for 3, and this consists of 2, 3, 5 and 6. How many items are greater than 3 and less than 4? Well, there are 4 of them. There are 4 items in there. So 2, 3, 5 and 6. 4 items, so the answer is 4. So it's a very simple technique, but quite useful. It's called a stem and leaf display. There are others. There's one called a box and whisker plot, and this also is very useful and widely used. It's useful and widely used, which I suppose goes together. Let's see how it works. We have the number line, so we start at 0 and we go up in tens. So 0, 10, 20, 30 and so on. Now, if we put a line down, we call it a whisker. This is a whisker here. Think of a cat and think of whiskers. So the whisker shows the lowest value. So we've got the lowest value here, just on the tip of the whisker. And at the other end, we've got this whisker over here, which shows the highest value. And in between, we've got a box. We'll just talk about that in a second. So here we've got 2 whiskers. We've got the lowest value here, and here we've got the highest value. We also have the median. The median is the value which has 50% above and 50% below. So 50% of the observations are to the right and 50% are to the left. So we mark on where the median is. The median, it's not an average. The average is the total values divided by the number of items observed. This one is the median. It's the middle value. 50% above, 50% below. We also have what's known as the lower quartile. The lower quartile means everything below it represents 25% of the observations. So 25% of the observations are below the lower quartile. So 25% below. We also have the upper quartile. This is 3/4 of the observations are below this, or if you like, 1/4 is above it. It's the upper quartile. So 3/4 are below it, and 1/4 is above it. And that really constitutes our box and whisker plot. Now let's have a look and see how it works. For example, the age of people in a cinema on a particular date, watching a particular film. So the youngest person, let's say, is 8.6 years old. So we'd mark the youngest person, just put the cursor onto the screen. That's the youngest person there. Oops, I've moved it. Sorry. Come off. That's the youngest person. And you can see it's below 10, so it's 8.6. So that's the lowest value. The oldest person is 74, and that's indicated over here. That's the top value. The median age, the middle age for the people in the cinema, 50% of them are below 37 years old and 50% of them are above 37 years old. So the median age is indicated here at 37. The lower quartile is 28. That's the lower quartile there. That one there. The lower quartile means that 1/4 of the people in the cinema are below 28 years old. 1/4 of them are below 28 years old. And the upper quartile is 64. It's over here. So 1/4 of the people in the cinema are above 64. And that is the box and whisker plot diagram. Now, let's look at some techniques for analysis. Well, one of the main techniques for analysis is the transformation of data. It's to improve interpretation and compatibility with other data sets. It's to make sure that the data fits other data sets and can be used easily. It transforms the data. It doesn't change the essence of the data, it just transforms the data, make it easier to use. It could, for example, enhance symmetry of the data and stabilize the spread, looking at the spread of the data. If the data is very spread out, a technique may be used to bring it closer together. It still keeps the data as it is, it just changes the scales in which we look at the data. It could improve the linear relationship amongst the variables. It transforms the data so that there's a different take on the linear relationship. It's still the same data. Just to illustrate this idea of transforming the data itself. So here's a set of data, 103, 124, 236, it could be whatever. This normally applies to very large numbers. I've only taken 3 digits here, but if we're talking about the national economy, the gross national product may be in billions, which is very large numbers and difficult to handle, particularly if we're comparing numbers which are very large with numbers which are very small. For example, let's say you're comparing the gross national product, which is in billions, with interest rates, which is in fractions, small fractions, say 10%, 5% or whatever. Now, what we need to do is to transform the data. So let's just illustrate it with this simple set of data here. Now, we call this our raw data. Now, we transform it by, let's say, creating an index into a set of index numbers. I'll just put the cursor onto the screen. So here we'd say, let's take this number as our base. So 236 is our base. So what we do is we take 103 divided by 236, which is 0.55. 124 divided by 236, 0.53. 236 divided by 236 is 1. 315 divided by 236, 1.33. So what we've done is we have converted or transformed the original data into smaller data, into a set of index numbers. And it's still the same set of data, it's just been transformed. And you can do this in various ways. This is just using index numbers. We could have used logarithms, or we can use various techniques just to transform the data, which is perfectly acceptable providing the users know what the data is and how it's been transformed. Now let's look at, very briefly, data mining techniques. This is the idea that we're trying to discover patterns in numbers. So we're trying to discern useful information in data sets. And these are normally held in databases. We want to look at how the numbers appear in the database and how they're clustered also. Are they grouped together in some way? And we'd want to have some sort of models to try and interpret these and how they're classified. These are all techniques which we don't need to get involved with here, but they do arise when we're looking at data mining, which simply means going to data sets to try and extract information, to try and find information about the information, to process the information, in other words, to try and see what the information is trying to tell us. The data mining process, well, normally we'd sample the information and then we explore it. And we'd use all sorts of techniques to explore it. We might want to simply plot it and look to see how the numbers appear when they're plotted on a graph. Or we might want to transform the numbers, or we might want to try to model the numbers to see if there is a pattern, some sort of trend line perhaps. We might want to modify them, as I said. Modifying means transforming. And we might want to get the best model, the model which works most effectively with that set of numbers. And then we try to assess the whole thing to see if it works. So data mining is associated with large data sets, and it's trying to make sense of the large data sets to try and give us an insight in what the numbers are trying to tell us. And that's all I'm going to do in this class. We've looked at two big techniques, two popular techniques, yet easy, the stem and leaf and the box and whisker. We've looked at data transformation and the types of data transformation that may take place and why it takes place and why we use it. And these will be preliminary before any investigation takes place. Any detailed investigation, I should say, takes place, and before certainly the results of that investigation are used for decision purposes. But that's all I want to do in this session, so thank you for watching.